Hello, my name's Ryan. I was in charge of the mechanical system for the project. Taking a look here first is the rotating assembly. The design inspiration for this came from European automotive transmission manufacturers, where they utilize a dual shaft design due to overall footprint restrictions inside a tightly packed transmission case, where there is a inner and outer dual shaft design. Our implementation utilizes 6061 aluminum for both of these shafts, for the outer and the inner shaft here. There is also two semi-sealed ball bearings to maintain alignment of the inner shaft onto the outer shaft, as well as a thrust bearing in between these two gears as shown here to reduce overall friction between those two gear pulleys as well. And to maintain alignment of both of these assemblies together is a pillow block support bearing here with a cast iron body. And to drive this rotating assembly, we utilize a belt drive system just to maintain required tension and to minimize backlash on the system, as well as improving smoothness in the overall motor driving system as well. Up next is our belt drive system. Inspiration for this came about from existing 3D printers on the market. They provide a relative good performance without the incurred additional high costs. We utilize modified billet aluminum gears, essentially gears that we just have to enlarge the bore diameter to fit our custom-made rods and drive shafts. We also utilize fixed tension belts, essentially a stretch belt without any use of any additional tensioners or any additional other spring mechanism to maintain tension on these belts. There is some adjustment within our motor mount plane with the slots in the bottom and this motor mount wall to adjust tensions on the drive belts of the system. And we utilize a pulley reduction here to improve the amount of torque that we are required to use for the project in maintaining overall arm movement and steadiness. The secondary arm drive belt system utilizes a 1:1 gear ratio to maintain overall strength and torque needed to drive our secondary arm. Now, taking a look at the dual arm mechanism of the project, the design inspiration for this came from the Arc Droid dual arm system, where it utilizes two arms that can be folded together to reduce the overall footprint for when the machine is in transit or when the machine needs to be moved. Two separate arms are both machined from 6061 aluminum bars, where their larger primary arm is attached to the outer shaft and the secondary arm is driven by the belt drive system of the inner shaft. For the project, two drawing attachments were implemented, which are then mounted onto the attachment arm, which is the 90-degree stainless steel bracket here, which is then attached to the secondary arm of our dual arm mechanism. First off, we have the laser module that is attached to a adapter plate that we developed with stainless steel standoffs due to the heat constraints of the laser module. That is then mounted to the attachment arm here. And then we also have a marker holder for a standard Sharpie permanent marker that is 3D printed with an actuator and spring mechanism that is demonstrated here, where the servo actuates the up and down movement of the Sharpie, as well as the spring component maintaining pressure onto the drawing surface as well. Looking at the mechanical system as a whole, we have two stepper motors driving our primary and secondary dual arm mechanism, and our attachment arm being mounted to the secondary arm holds our tooling, such as the marker holder as shown here, or we can swap out to the laser module as well.
Hi, my name is Carlos Carvajal, and I did the majority of the control design for the robot that we made. So our design was based off a 2 degree of freedom planar manipulator, which basically means we have two arms, which are here, link 1 and link 2. Um, we had to be able to um, change from the motor angles to the joint angles, and so we can see here that we go from phi 1 and phi 2 and map those out to theta 1 and theta 2. And that way we can properly do motion planning and trajectory planning. This is all taken care of by Linux CNC, which is the software that I use to be able to run G code to be able to actually move the robot how we wanted it to move. So based off of that, um, we then go to the inverse kinematics. Here we see the actual function that Linux CNC uses for the inverse kinematics. And so I won't really go into details, but then here at the bottom we can see that the joint angles um, are reliant on a combination of the motor angles. And then as well for the forward kinematics, we see that they are properly handled as well, where D2 was a certain length for the first joint, or for the first link 1, and then D4 was the length of link 2, and that way we can properly map out exactly where we're going to be on whatever surface we're drawing or cutting into. And so with the inverse and forward kinematics, the basic gist of it is the forward kinematics work by going from the base of the robot all the way to the end effector, which in our case is either the laser or the pen that we were using. And then the inverse kinematics, the way it works is it goes from the end effector down to the base. And so that one is a lot more complicated, and that's why we saw that the code was a lot longer. But that basically just calculates the actual joint angles themselves. Forward kinematics are pretty trivial. There's a lot of ways to solve them. Inverse kinematics are a little bit harder, but because we had a pretty basic robot, um, it wasn't too difficult. So I just had to change a couple lines of code from what Linux CNC already had for some previous robot designs. And we actually got the robot to work pretty well based off of that. And then here we can actually see a screenshot of the Linux CNC software. And so here we can see that our G code is displayed in the bottom text box. And so it goes line by line, and we can see that it then maps out our like our actual points on the GUI interface here. And so that little cone is where we start. That's our homing position. And our robot is actually all the way, like the base of our robot is, if you follow that blue line, it's all the way at the end over there. And so this is basically where our robot is extended all the way. And so once we start the program, our cone starts moving, hits the center, where the U actually intersects with the blue line. And then from there, it starts mapping out um, the actual U in real life. And so that's how we started getting the pen plotting and the actual laser engraving with the laser diode. Um, and then up here we can see in the top left that Linux CNC is controlled by the X, and then we have to toggle the power on, and then we could bring in G code slices that we want to use. But yeah, that was the basic gist of the controller.
Hi, I'm Aiden Case. I was in charge of the GUI for this project. The main goals for this project were for the graphical user interface, were for them to be very easy to use and straightforward, as well as touchscreen capable. This would allow us to use it with just our fingers as opposed to with like a stylus or a mouse. We also want this to be self-contained, so that way we could keep this entire device as portable as possible, rather than bringing around an extra computer or something. For software, we used a library called LVGL, or Light and Versatile Graphics Library. This is built entirely in C, and is designed for MCUs. This meant that when we used it on a Pi, it would be run really quickly and be very responsive. However, it also meant that we had to port it over for use on the Raspberry Pi as opposed to just using one of the built-in ports. That took a little bit of time, but thankfully we're able to use the display and touchscreen drivers we needed to, thanks to the SDL library, or SDL2. This is a fully customizable GUI, including colors, layout, everything like that. and also because it's built in C, allows us to interact with the command terminal in Linux. It allows us to do stuff with the GPIO, which was really helpful for our project. For the hardware, we used a Raspberry Pi 4B. This was chosen because it's plenty powerful and also relatively cost affordable. We chose this because for its networking ability, namely Ethernet, as well as potentially Wi-Fi in the future, and its I/O, such as that USB port that we used for both uploading files to and interacting with the touchscreen. We also chose this for speed, like I mentioned before, with LVGL being a library for microcontrollers. It meant that our GUI was really responsive because it's running on a much more powerful computer. We also used a 7-inch touchscreen that we sourced. This was a 1024 by 600 pixel display, so fairly high resolution, especially for the cost, and also was pretty bright. Its other benefit was that its touchscreen was controlled through the USB port, which meant that we could power and control the touchscreen with drivers through one cable, which simplified our wiring quite a bit, and also allowed us to interact with just use one SDL port in our LVGL library.
For our PCB, we wanted to run 3 operations. We wanted to run our Raspberry Pis. We wanted to power our motor drivers for our motors, and we also wanted to provide a charging system for a battery that we were going to use to power the Pi and drivers. So we went through various parts to figure out which part was best, and for our motor drivers, we decided to go forth with the TMC 2209. What this driver had specifically was just had our desired current and our desired voltage, so we had enough to power our arms. We also wanted to ensure that a 12 volt was going to be on the output, so we decided to add a few voltage regulators to ensure that we can have that 12 volt. And we also added an external buck converter that had stepped down from 12 volt to 5. That way that 5 volt can power our Raspberry Pis. For our charging IC, we decided to go forth with our BQ243 product. What this basically did was to allow to charge our battery that we were going to use to power the Pi. This ended up not working, as the IC we chose only supplied a maximum of 5 volt, while we needed a supply of 12 volt. So eventually the idea was just scrapped. Regarding our current overall on the board, we needed a total current of 5 amp. That way we can do all our operations. However, we only had a maximum of 1.5 amps. And in order to solve this situation, we decided to power our Raspberry Pis through an external power supply. And for our board, we just powered our motor drivers. That way we can ensure that every system has enough voltage and current to power our whole system.
All right, so here's a demo of our PortaGuide GUI. So we've got demos. We're going to do a laser demo, and we'll do this complex one. Start this to send the file across. The laser will start moving. Then try to get this to focus. We'll start drawing. As this is going, you can also see that we have our program is running with a quit button. This quit button will function as a full e-stop that'll completely reboot both systems. And that's done. We're gonna leave it in there, and we're actually gonna run it a second time just for a little better result. But you can see our program is done running, so we can start it again. Okay, now our second run has just finished. Pull this out. We'll be able to see that we have 2 runs that basically perfectly overlapped each other on a U. All right, next demo we have is for our pen attachment. So we'll go to pen demos and do the same one. Complex, if you want to start it, Carlos. There you go. So this one has the actuator as well in order to move the pen up and down. And we can also move this one a little faster because pens draw quicker than a laser. And the program finishes. All right, going through the GUI. This is also touchscreen. I'm just going to use a mouse that we can see better. We have an info screen. This has information about the project. So, who did it, why we want, why we came up with the idea, what can it do, what the four main components were, and then who created it. We also have a help guide, which is just a very simple, frequently asked questions. We can add more to this really easily if we wanted to. We have new project, which we can select from a USB for. We don't have a USB up here, but you can see we have this test file. Basically, this will just allow us to essentially upload a file to PortaGuide for it to be run. And then we also have the demos, as you saw earlier. We've got a line demo, a square demo, circle, oval, star, and complex. Complex being that U that you saw. And then we have the same things for a laser, with the only difference being that we have a PWM in order to raise and lower the pen, as well as the pen moving a lot slower or a lot faster than the laser. Okay, we can also try out our e-stop functionality. So let's just say we want to run this square demo. Okay, we'll see that the program starts running. We're not going to turn the laser on for this one, but if I press this quit button, it'll actually reboot this Pi, which completely stops the robot mid-cycle. Which, if we open this up, we can also see that the robot is free to move. And then this Pi will reboot, which will then send a signal to this Pi once it is done rebooting.
We about to turn it on.